Our next great discovery occurred in the 19th century when many chemists believed that organic substances from organisms or living things were somehow different from inorganic substances, from non-living things. But that was about to change. In 1828, Friedrich Wöhler was working in his lab when something caught his eye.
Wöhler had placed two inorganic chemicals in a beaker, potassium cyanate and ammonium sulfate. Now when he looked at the beaker, it contained a gram's worth of small, white, needle-shaped crystals. What made this remarkable was that Wöhler thought he'd seen these exact same crystals once before, but with an important difference. Those crystals had been organic. He had crystallized them while studying the chemistry of various substances found in urine. To make sure he wasn't mistaken, Wöhler analyzed the new crystals. There was no mistake. These crystals were the same as those he had isolated before.
He had made urea, which was something that had come out of a living thing. He had made it out of inorganic substances. Later he said, in a personal letter, not in a paper he wrote about it, that I have made urea without a kidney. And he knew what he had done.
Meet Roald Hoffmann, winner of the 1981 Nobel Prize in Chemistry for developing a theory to explain organic chemical reactions.
So why is this discovery of artificially making urea, why is that a great discovery?
You know, there comes a time when you need a discovery, and sometimes a single one, to cross a border, to break down a wall. This is what this discovery was. It's not that it was so important in and of itself, but at the time that it came, this simple making of urea out of two inorganic chemicals, when it came, it caught people's attention. The whole story of the discovery is about the underlying basis, the building blocks of all matter, organic and inorganic, being the same, atoms.
If these Lego bricks had existed in the early part of the 19th century, chemists could have used them to help illustrate something they were seeing in their experiments. A phenomenon that led to our next great discovery. The atoms of particular elements, such as sodium and chlorine, seem to combine with each other according to fixed ratios. It was this combining power of atoms that inspired German chemist August Kekulé to develop a system for visualizing the chemical structure of various molecules. Kekulé represented the atoms by their symbols, then added marks to indicate how they bonded with each other, like links in a chain. It was a simple yet elegant formula. Chemists now had a device for clearly illustrating the chemical structures of the molecules they were studying. There was just one problem. Benzene was the only known chemical that would not fit Kekulé's formula. Benzene's chain of carbon and hydrogen atoms required more combining power than the formula would allow.
And all these organic chemistry professors are puzzling about it and offering different explanations. And one of them, August Kekulé, sitting by the fire one evening, falls asleep and starts to dream about a snake. And if you think about a snake, what Kekulé dreams of is the snake catches its own tail. And if you think about this, maybe the thing is a ring. And that gives you an answer to the puzzle.
The 6 carbon atoms of the benzene molecule weren't linked in a chain. Like the snake, they formed a ring, each with a hydrogen atom attached, with alternating single and double bonds. Within a short time, Kekulé's insight was confirmed, and its effect was revolutionary. Chemists knew that all organic substances contained 1 or more carbon atoms in their molecules. With Kekulé's discovery, they now had the underlying formula to explain how carbon combined with other molecules to form a world of chemical compounds. The modern era of organic chemistry was born.
Now, with this thing being so simple, that is to say, the snake bites its tail, why is this considered a great discovery?
Here is a recipe for new drugs, new medicines, new understanding. If you go back in time, in Dalton's day, a couple of hundred compounds. Soon it's a couple of thousand. Soon it's 10,000. Astonishing. Soon it's 100,000. Last year, 15 million new compounds were registered, all built on this simple template. This is a work of genius.
In 1869, a Russian chemistry professor named Dmitry Mendeleev was writing a textbook for his students when he began to wonder how he could best explain to them the 63 elements that were known at the time. To help formulate his thoughts, he constructed a card for each element. On each card, he wrote the name of the element, its atomic weight, its typical properties, and its similarities to other elements. He then laid the cards out like a game of solitaire and began arranging them over and over, searching for patterns. Then came the moment of discovery. Before him was something extraordinary. The elements fell into 7 vertical groupings. Each periodic grouping had members that resembled one another, both chemically and physically. Mendeleev had discovered the periodic table of the elements, a map showing how all the elements related to one another. A map so precise that Mendeleev believed he could also use it to predict the existence and properties of 3 elements no one had yet discovered. One would be like boron, he said, one like aluminum, and one like silicon. Eventually, the elements were discovered, and Mendeleev was proven right.
There was actually a little bit of controversy because a German chemist named Lothar Meyer had come up with roughly the same idea. But Meyer didn't quite have as much courage. So that's actually an interesting thing. Here is this German who comes up with the same idea of periodicity, of which there were hints already before, but he doesn't make the predictions that Mendeleev does. So here we see the power of a risky prediction in having people accept a theory. There is nothing more powerful than making a prediction that's not obvious.
And then have it come true.
And have it come true.
Yeah.
The periodic table is our icon. I mean, it's what we associate with chemistry. You go into any chemistry room, you see it.
Why is the periodic table of elements significant? It forever changed the way that everyone would learn and understand the elements. The periodic table of elements is to chemistry as notes of music are to a Beethoven sonata. In honor of Mendeleev, his name is now literally attached to the periodic table. The element 101 was named after him. It's called Mendelevium.
It's not only chemists who like the periodic table. I hear you carry one around.
I do carry one, yes, sir.
Show me.
You never know. And I see you use it a lot.
Let's see.
It's a small one.
So I'm going to give you a test. What is under nitrogen in the periodic table?
Nitrogen is 7.
Yes.
I have to think a second.
Under
sulfur.
nitrogen. No, you're wrong.
Oh, God. That's why I carry the
You're
thing.
one off. It's phosphorus.
Oh, phosphorus.
Phosphorus
No,
is
15.
right.
Phosphorus is 15?
Yeah, you have to add 8 at that point.
See, that's why I carry it. I can't remember. So it's 7 plus 8, 15 phosphorus. Okay. There's a pattern there. I get it now.